of the maximum displacement of a particle from the equilibrium position, either negative or positive, is called the amplitude of the wave. As the force between particles is the same, it can be seen as an indication of the energy of the wave. The greater the amplitude of the wave, the more energy is stored in each oscillation. This energy is equal to zero overall, as the oscillations that make up a wave have zero displacement overall. Both the positive and negative displacements add together to equal zero displacement. We have dealt with non-moving oscillations so far. We have yet to talk about the motion of this oscillation through the medium. If we have a force that drives this oscillation, maintaining the initial displacement of our first particle, then this particle in turn makes the particles around it move. If this original particle is driven upwards and downwards, it in turn will drive the surrounding particles upwards and downwards, as they are connected through bonds. This motion of particles and surrounding particles is called a wave. The particles move up and down in time with the original motion. The relationship between particles within a wave are given specific names. The number of times a particle is moved up and down at a certain place in a given time is called the frequency of the wave. If we treat one wave as the movement of one particle from its equilibrium position back to its equilibrium position, but moving in the same direction, then we can measure the length of a wave. Instead of the equilibrium position, we can use the maximum displacement, as this is easier to see. The maximum positive displacement is called the peak value. The maximum negative displacement is called the trough of a wave. The point between one peak and the next peak can be used to describe the profile of one wave. The time it takes for the particles to move from peak height back to peak height is called the time period of the wave. The number of waves passing a fixed point in this time is called the frequency, and is inversely proportional to the time period. The physical distance between one peak value of a wave and the next is called the wavelength of a wave, and how quickly all these peaks and troughs and displacements move relative to the background medium is called the wave speed. The speed of the wave through the medium is linked to the bond strength between particles, as is the wavelength and frequency of the wave. However, the speed, wavelength and frequency of a wave are all linked together via one equation. If a wave is moving quickly, it covers more distance between peak and peak with reference to the rest of the medium. This means that the wavelength of a wave increases with wave speed, so they are proportional. The faster the wave is moving, the more waves per second pass a fixed point on the medium, so frequency is also proportional to wave speed. Combining these two aspects together tells us that wave speed is equal to wavelength times frequency. Don't forget that frequency is inversely proportional to time period of a wave. This means that time period is also inversely proportional to wave speed. The faster a wave travels, the less time it takes to move from peak back to peak.